I will be talking about my PhD project today, which is on the automatic detection of syntactic differences. And I'm actually not quite there yet, so this is aptly called Towards the Automatic Detection of Syntactic Differences. I'm Martin. I'm from Leiden University. I'm a PhD student there, and I will be visiting here until Christmas. So today, as I said, this is a very vague slide, but I will get into this. I will just talk about my PhD project, which is called Detecting Syntactic Differences Automatically, which we abbreviate to DESDA. So first about the whole project a little bit, and then its phases in a little bit more detail. But first a little bit about myself, because I don't know anyone except for Dan here. I'm Martin. I'm a PhD student in Leiden, and I will be here until Christmas. I did the LCT Masters a couple of years ago, which I think most of you actually know, because Prague also offers it. And I'm doing my PhD on the detection of syntactic differences under Professor Chef Barbiers and Professor Jan Oudijk, and also Dr. Stephanie van der Pas. So yes, a little bit on my project. What we want to do is to automatically find differences in syntax or even morphosyntax between languages. And we will be using parallel corpora for this, because we think that parallel data is actually very useful for this, because you can really point towards the differences. And we want to do this cross-linguistically. And this brings up a lot of problems, actually, because we need to deal with all different tag sets and differences in annotation guidelines. And there's, of course, a danger of circularity, where you actually, instead of comparing syntax, you actually start finding differences in the annotation. And our eventual goal is to have a big pipeline, or at least a pipeline, for linguists to guide them in their research. But why do we want to do this? Well, as linguists, we are interested in language, in the range and variation of human language, and especially in comparative syntax, we want to find or have an understanding of the underlying structure that all languages share. And we want to answer questions such as, which abstract syntactic principles do languages share? Are there clusters of syntactic variables that can be reduced to one underlying principle, so that if one changes, all of them change? And just in general, what are the limits of the variation that we find? But there is a problem. We work with big data, and it is incredibly big, because there are 6,500 spoken languages nowadays, and we also deal with dead languages, so there are just too much data, because they can all create an infinite amount of sentences. So the result of this is that linguists or syntacticians, in selecting their data, already often have a vague idea of what they will find in their data, which can lead to a bias in their data. So what we want to do is to actually make an unbiased pipeline that can process up to millions of sentence pairs in multiple languages at the same time, to speed up this process significantly. So there's a couple of phases to this. First of which is, of course, the data pre-processing. This bit is actually finished. We've developed a filter that selects parallel sentences that are actually suitable for syntactic research. And then you can actually detect differences on a macro level or a micro level. So you can either aggregate all the data first and then start finding differences between the entire data, or you start looking sentence by sentence, find the differences between the sentence pairs, and then actually aggregate the differences and say something about the languages as a whole. This bit I'm working on right now. I will be talking about this today, and these two bits are for future. And after the micro bit, I will do some evaluation, some real linguistic things, where we will compare the results of the pipeline with differences described in the literature. And especially, we will look at the Germanic languages, because they're very well described and we know what to find, right? So, Today, in more detail, I will talk about my project, but then phase one, the pre-processing, about the filter that we made, then phase two about the macro level approach, where we will use the minimal description length principle, and then we'll very briefly touch on phases 3 and 4. All right, so this is actually a recently published paper. I think it's actually still to appear, to be honest. But yeah, a filter for syntactically incomparable parallel sentences. So, parallel data. So as I said, we will be working with parallel data, but this is, it is a blessing because there's so much data, so much information in there, and it is very useful for what we want to do. And we are specifically using the Europal corpus, which is very big, and is actually the proceedings of the European Parliament. I think most of you will be aware with this. Contains 21 languages, 5 of which are Germanic, and then more than 11 million sentences and almost 250 million words in the Germanic languages only. So it's really an abundance of data. But it is actually a blessing in disguise, because the problem is that there is, it can be noisy, very noisy. There's a lot of free translations, wrong alignment, and everything. And if you start mining for syntactic differences from the wrong alignments or the free translations, you will end up with differences that are not really interesting in the end for syntacticians, right? It will be a little bit noisy. Here's actually an example where, let me see if this works. Yes, it does. So in English it says on the subject at hand. In German they say zum Thema, and in Dutch we say dan nu het eigenlijke onderwerp, which are all syntactically completely incomparable, but the meaning is somewhat the same. So we want to get rid of these kinds of things before we start finding syntactic differences. So we need a filter, and since the data are so big, we need to automatically select suitable sentence pairs before we can detect actual syntactic differences. And we want to do this by establishing some sort of threshold beyond or below which sentences are no longer considered comparable. And there is, this is, and here we are touching on a gray area, because we say we are filtering out sentence pairs that are syntactically different in order to detect syntactic differences, right? And this brings us to the question of what syntactic comparability actually is, and this is almost a philosophical question. And I think I can fill an entire afternoon on this. I won't, don't worry. But just a few examples. So the first one, that is what will make us strong. These are actually real examples from the Europal corpus, except for the last one, by the way. That is what will make us strong against the Dutch. Dan zijn wij sterk. These are, which is literally, then we are strong, is incomparable. We don't want to use this. I think you all agree. I hope. Yeah, I see someone nodding. Thank you. The other one, the second one, pertains to idioms, which are interesting in themselves, but can show very different syntactic structures. And if you start, I mean, they mean the same thing, but if you start extracting syntactic differences from them, you might not find what you actually want to find. So you might want to get rid of these examples, for example. The third one is just a paradigm shift from active in English to passive in Dutch, while there is really no reason actually to put it in passive in Dutch, because the active sentence is just as natural. So you might want to get rid of this because it doesn't tell us anything about the potential of the language. But the last example actually does tell us something about the potential of the language. This is English against Finnish, where English has passive and Finnish has active, but it has to be translated into active because in Finnish you cannot have a passive when the agent is actually animate. So this does tell us something about its potential. So it is a very difficult question, and it really depends also on your research purposes and your language pair and everything, and therefore we decided to give the option to the users of the filter to actually manually set the parameters of the filter, and also to use their own data set completely based on their own wishes or demands, right? But for our research, we said, our rule of thumb at least was, if all content words in sentence A have an alignment in sentence B, and also the other way around, where you ignore the punctuation, and also if there is no paradigm shift from active to passive or whatever, and if there's no idiomatic constructions in one language, or a cleft or whatever in one language, ignoring word order, this is actually important, then the sentence pair is considered syntactically comparable. Then we don't want to throw it out, right? Okay. So we took some data. We took 3 language pairs from German, English, Dutch, from the Europal corpus, and we labeled 400 sentence triples. So all the sentences were present in all 3 languages, right? And we labeled all pairs for whether they were or were not syntactically comparable, just binarily. And they were tagged by multiple people. And these are the distributions. So in German English, we had 131 sentence pairs that we considered syntactically comparable, but 269 to be incomparable. German Dutch, 106 versus 294, and English Dutch, 173 versus 227. So you immediately see it's very unbalanced, which can pose a problem. So what we did, we explored 4 filters, 4 techniques, 4 approaches, and tested them with different parameters, and we looked at a Levenshtein distance on part-of-speech tags, because it is a very simple approach. We looked at the sentence length ratio, which was also a very simple approach. We looked at the graph edit distance on dependency trees, and we looked at a combination of the 3 in a logistic regression. And also, and I won't talk about this today, but we also looked at doing things with word embeddings and word vectors to see if they are the same, but it really did not work above chance level at all, so I left it out. So the Levenshtein distance on the part-of-speech tag, so this is the minimal amount of edit distances, edit operations, sorry, to get from one sequence to the other, and it is, it's a very well-established measure in computational linguistics, so we thought, therefore, the bare Levenshtein distance, we should use this as a baseline, because anything should work better than this. And we also tweaked it a little bit with some options where we ignored function words based on the part-of-speech tags, and also whether or not to allow for transpositions, which isn't normally the case for Levenshtein distance. There's one big concern, of course, with the Levenshtein distance. Levenshtein distance is just completely linear, which means that if there are big phrases moving around, if you're comparing an SVO language to an SOV language, you might end up with a problem if big chunks move around. So, for example, if you take English and Dutch, there's 2 phrases moving around. If Levenshtein doesn't know that the phrases are moving around, the edit distance will be 4. If it does know, it will be 2, right? So this is really a bit of a concern with the Levenshtein distance. And then the Levenshtein distance, right? This approach gives us a value below or beyond which sentences should not be considered syntactically comparable. Now, the sentence length ratio, we looked at the relative sentence length in terms of percentiles, and this also is computationally very cheap, and it is what we, in terms of percentiles, means that we throw out the n% sentence pairs with the most extreme sentence length ratios, right? So if a sentence in one language is 3 times as long as the one in language 2, throw them out. They're probably not considered equal, right? And we also experimented with ignoring function words based on part-of-speech tags, but there is a big concern. It does not use any syntax at all, and it is very coarse-grained. Then we looked at the graph edit distance on dependency trees, which is like this Levenshtein distance, but then on trees. And this has the advantage of being insensitive to transpositions because we work with unordered graphs. And we also worked again with the options to ignore function words, also to include morphological features because the parser just gave us the morphological features as well. But there's a few concerns with this as well. It is very dependent on parse accuracy. If your parse is off, then you have a problem. It requires a parser to exist in the first place, which is also sometimes a problem. And it is computationally very expensive because the graph edit distance, I think, is an NP complete problem, or at least hard. And then we looked at the combination filter where we took the values of the outputs of the previous filters as inputs for a logistic regression model. And the options were just any options for any combination of options of the other filters, right? It has one drawback. It really does need a training set, which isn't always there. Okay. But then how do we find a threshold? Because we're now, we get values. How do we find the best threshold? Well, we used a RSC curve for this, where you plot the true positive rate against the false positive rate against, at various threshold values. And then the best threshold value or setting is in the top left corner over there, which is calculated with the J statistic. And it's very useful, it's very practical because it is not affected by unbalanced data. And its performance of a classifier is then measured by the area under the curve. The bigger that is, the better it works, right? Which is between 1 and 0.5. If it is 0.5, then it is just chance level. Okay. How did we evaluate the filters? Well, we tagged and parsed everything in universal dependencies with UDpipe. And when we ignored function words, we just looked at any combination, every combination, I should say, of closed set part-of-speech tags from the UD program. And then the results were reported in terms of AUC, the best threshold, and parameters. And for the combination filter, we plotted the RSC curve with the probability as the threshold. Okay, now, what did we find? This is the baseline, so this is a completely simple, bare, classic Levenshtein distance on part-of-speech tags. And it doesn't perform all that bad with about 0.75 area under the curve. But what we do see is that the thresholds are very, very divergent for all language pairs, right? So that is not really ideal. Then we tweaked a bit more with the Levenshtein distance. We improved slightly on the baseline, but yeah, the parameters were still very divergent. The thresholds were very different. The to be ignored functional material was not the same for all of them, although we do see that German English and English Dutch use the same sets, which is interesting, but then Dutch English does allow for transpositions, but German English does not, so that is a bit strange perhaps. The sentence length ratio does not perform that well at all, which we expected, right, because it doesn't use any syntax. And then the graph edit distance did not really improve on the baseline either, but what we immediately saw is that the parameters were extremely stable throughout all language pairs, which is very gratifying. So we found that a threshold of 4 or 5 works best for all language pairs. Don't ignore anything in terms of function words, but do ignore morphology. So that was very interesting to see. And then the combination filter obviously worked, well, not obviously, but it worked best because it uses more information. So it is slightly to be expected. I'm not going into detail what it selects, but yes. So a little bit, so discussing this filter, so the results suggest that it is an incredibly hard task to do. That is one. But we believe that the filter can be used to select material suitable for syntactic research, definitely. But the results furthermore also suggest, which is funny to see, that German, English, and Dutch are rather similar syntactically, because if they were not, then there would have been a larger gap between the Levenshtein distance and the graph-edit distance. And on the other hand, the Levenshtein distance shows very diverging parameters, suggesting dissimilarity, right? If they would have been completely the same, the parameters would have been the same, probably. So the combination filter gave us the best results, but it requires a training set. A grid search is expensive and the risk of overfitting is very high. But if you don't have a training set, you can still achieve some reasonable results with the graph edit distance, which is very robust in its settings, which suggests the default, actually. And also is expected to outperform the rest more clearly when it is provided with perfect parses. Okay, so that was on the filter. That was phase one, so now we have some data pre-processing. And now we're actually going to mine for syntactic differences. Let me take a sip of water there. A lot of abbreviations in this title. So detecting syntactic differences automatically using the minimal description length principle, work in progress. That's what it means. Okay, now, so this is the macro approach. This is, we look at the data in its totality and then find the differences. And this is, as I said, the second phase, and we're actually mining for syntactic differences now. We build on Wiersma and others who extract syntactic differences from non-parallel data from the same language using n-grams, right? And they do a permutation test to rank their the significance of the differences. But we find a problem. They have a fixed n for n-grams. It is not between languages, and they don't make use of parallel data. So what we are investigating is to actually whether we can apply the minimal description length principle in this task, because this circumvents the fixed n and it can be used between languages. And eventually our goal is to make a tool that guides linguists to possible differences. So the minimal description length principle is actually a compression technique. And we say if you can compress something, you can learn something. And what it does, it finds patterns in the data to describe it using fewer symbols than needed to describe the data literally. So what it tries to do is actually find a code table such that the size of the code table plus the size of the data given the code table is as small as possible. We want to compress it as best as possible, yeah? And what you then get is actually a code table with patterns that are characteristic of your data. And we are using Squeeze in this. Squeeze is an algorithm developed by Tati and Freke that mines patterns in sequential data using the minimal description length. And its novelty is that it can actually, it allows for gaps in its patterns. So for example, they ran it on the JMLR corpus and they found this is the top 10 of most characteristic patterns in their data. They found support vector machine, machine learning, state, art. So this is a gap that was actually allowed by the algorithm. Dataset, Bayesian network, large scale, nearest neighbor, a decision tree, neural network, cross-validation. And we have a very, very clear understanding of what this corpus is about, namely machine learning. And this is true because JMLR is actually the journal for machine learning research. So this is actually, it really worked. It's very cool, I think. And what we thought is, can we then actually use Squeeze to detect structure in language? So as a little proof of concept, what we did, we ran it on Dutch words on a character level, and what we found were stems and productive morphemes. So that was really quite cool. But then what we thought is, let's push it a little bit and let's go for syntactic structure in this. So what we do, we generalize over word types by part-of-speech tagging. We change the entire corpus in a bunch of sequences of part-of-speech tags. Then we do the Squeeze. And what we should get is a bunch of part-of-speech tag patterns that are characteristic of that language, because they appear a lot, right? So before we do this, let's think very briefly on what we expect to find in English. Well, first of all, we expect to find determiner noun because it's there all the time. For example, the man, a country, this kind, or adjective noun, maybe with the determiner in front of it, a small mistake, good opportunity. Apposition, determiner noun, so an apposition is just a preposition, but then more general. By the committee in the morning, auxiliary with a verb after it, can see, have been, might have, might collapse, whatever. Particle verb, to go. I think you'll all agree these little bits, these little chunks are very characteristic of English syntax, English sentences, right? But what do we actually find? We do indeed find these things, which is very cool, because we find apposition, determiner noun, determiner adjective noun, particle verb, determiner noun, pronoun auxiliary verb, noun punctuation, which is interesting, pronoun verb, adposition, determiner adjective noun. So these, you actually find structure in your data using the minimal description length principle. And this is, I think, very cool. But now, how do we actually find differences with this? Yeah, so we have one big assumption. We say that if there is no syntactic differences between two languages pertaining a given, to a given syntactic pattern, right? The distribution of that pattern must be the same in both languages. That is to say, if a syntactic pattern occurs in a sentence in the one language, it should also occur in its translation in the other language, if they are the same, if there's not a syntactic difference. So, what we do, we leverage the parallelity of our data, and we count for every pattern how often it actually occurs in every Dutch, for example, sentence, where it does not occur in English, and also how often it occurs in English, but not in Dutch. So kind of true positive, false positive, so you get a table like this. So you look at every sentence and you see if determiner noun occurs in English, yes or no, and in Dutch, yes or no, and then you get a confusion matrix over there. And these values are interesting. And then we do a McNemar test, which is actually a chi-squared test for a paired nominal data. So, in summary, what we propose is you run squeeze on two parallel datasets of part-of-speech tags to discover characteristic part-of-speech patterns. Then you merge those two lists. And for every pattern, you count the non-matching occurrences in a parallel dataset with a small asterisk, because it is actually important to note that it does not have to be the same dataset. Then we do a McNemar test for every pattern, and we return the most significant differences. Then we do some pretty visualization, which is work in progress, unfortunately. And then we go back to the data to see if those differences that it found were actually really differences. It points us towards something, and let's see if it is actually correct, right? So in our experiments, we looked at Dutch, English, and Czech. So Dutch and English was really a bit of a sanity check. And Czech was just to explore the potential of the method. I don't speak any Czech at all, so this was really interesting for me. And in step one, what we did, we took the first 10,000 parallel sentences from Europal to make sure that the data were homogeneous. And it's not a lot of data, but it is definitely enough. And then we count in the filtered version of the 10,000 parallel sentences. So we took our own filter, ran it on the 10,000 sentences. So, in step one, we ran squeeze to discover the characteristic part-of-speech pattern. So in English, we already saw these. You find adposition, determiner noun, which you also find in Dutch, interestingly. Determiner noun, both in Dutch and English, adposition noun. So these all make sense to me. I don't know about these. Maybe these make more sense to you. I don't know. I don't speak Czech. I looked at the data a little bit. I think this is correct, right? So what we find in English is determiner, adjective, noun, but in Czech we found the pattern without the determiner because you don't have articles. Am I correct? Yes. Okay. So I think this is interesting in itself, but then we actually start looking for the differences. We ranked it on the chi-square value. The higher that is, the more significant the difference. And these, I can tell you, are incredibly significant. So for Dutch English, ex-punct is the most significant difference, which I'll come back to this, but it is not interesting. Then we find auxiliary verb and then some auxiliary verb adposition, noun with it, which do make sense, actually. I will come back to this as well. Determiner noun, very high, unexpectedly, and then a few more. And let's have a look at Czech and English as well. Determiner noun is incredibly high, because in Czech there's no article. We really expect to find this. Pron aux is also, it also makes sense because you can drop the pronoun, if I'm not mistaken. Then a few more, which also make sense. And let's actually look at that. Let's go back to the data, step 5. So in English, Dutch, as I said, auxiliary verb, it makes sense because there's a difference in the use of past tense. So in English, you have a lot of have been, has seen, where in Dutch we just use one word. And also it has to do with word order because in subordinate clauses in Dutch the auxiliary often comes in the end and the verb does not. Particle verb also makes sense because English uses to much more than Dutch does te, which we barely use at all. Determiner noun, as I said, surprisingly to me at least, Dutch uses much more nominalizations where English uses verbs. I really didn't know this, so this is quite a find for myself. And as I said, ex-punct is not interesting. It just turns out to be a difference in tagging in the UD pipe. It just contrasts with non-punct. But it is nice to see that we do still find it, although not interesting to a syntactician, right? Because it is a difference in the data. And then looking at Czech and English, as I said, determiner noun, Czech has no articles. Particle verb, Czech does not have a particle like to. Noun, adjective, punct, I don't know. In Czech, adjective sometimes comes after the noun, I read somewhere. Is there more going on? I don't know. Apposition noun also makes sense because English uses more prepositions because English doesn't have cases. So I do think that this is very, very interesting, very useful, but there are still some points of improvement that can be identified because it is still a work in progress. For example, the ranking criteria. There is a lot of overlap going on, as you could have seen, I think it's 2 slides back. Yeah, all of these start with auxiliary verb, and why could we somehow get rid of these 2 and just say, okay, it's just the difference is in auxiliary verb and not in the other 2, right? Could we do some nice statistics there? I don't know. And then the interpretation of the patterns can be incredibly hard, especially since they allow for gaps. And this could be the case with the Czech noun, adjective, punct. Maybe there are gaps between those tags that we don't see that would make it to make more sense. I just don't know. So the interpretation can be incredibly difficult as well. And I think this we can help the interpretation with some pretty visualization, but I have no idea how to do this. I hope some of you might have an idea for this, because I really don't. And then there's still the question, should we actually use our filter? Because I tried it with both the filter and without the filter, you get slightly different results. Both are useful and interesting, but they are different. And what does it tell us? Should we filter? I haven't decided on this yet. So concluding the MDL part, can MDL be used to detect syntactic differences from parallel corpora? Well, we think yes, we can. I just showed you that we did. And I have shown that we can retrieve meaningful differences that we expect to find, and even differences that we did not expect to find but are still useful. And it is exploratory in nature. It is made to guide the linguist. It gives you suggestions of where to look. But it is important to note that it does not give you all the differences, and not only differences either. Right? So it does also give you things that are not interesting, but it misses things as well. As I said, it's still work in progress, but we're almost there, and it is, I think you'll agree, promising. And then I'll now briefly touch on the future. So I have 2 more phases left. As I said, the micro approach, where we look at the data sentence by sentence, then aggregate the differences and look at that as a whole. I have a few ideas on how to do this. Maybe we can discuss this later on. Some word or tree alignment, and then detect the points where the alignment isn't one-on-one. We probably need our filter, right? Maybe there's some morpheme alignment. I don't know. Maybe we can do something with that. Is there a way to align hierarchically, where you say, okay, so the whole phrase, this phrase is aligned to this phrase, and within that phrase, these words align to these words? That would be interesting. But there is still a danger of circularity, because you will actually maybe just compare part of speech tagging. So what I want to do is actually find a way to circumvent the part of speech tagging and the supervised parsing altogether, and have the computer figure it out on itself completely. So I have questions like, can we do some word or phrase embedding only on a syntactic level where you completely ignore the semantics, or can we use unsupervised parsing or clustering of words based on morphosyntactic behavior? I don't know. I'm thinking about this, and this is actually my main goal during my stay in Prague, which I forgot to mention. I will be here until Christmas, so yes. And the last phase will be then to compare the results from our pipeline to existing literature, and then compare what we see. Do we find everything that was already found? Do we find more that was not yet described? And we will focus, as I said, on the Germanic languages, because they are very well described. All right, so that's it from me. Thank you very much. This is the bibliography. And then I made this with some nice alignment. All right, thank you very much.